Good morning, participants. On the occasion of 103rd birthday celebrations of Dr. Komaravul Chandrasekharan Garu, our department is conducting a 5-day international faculty development program on applications of mathematics in various fields with innovative approaches. On the first day, Dr. N. Sudhakar Garu, Professor, Department of Computer Science, Bapatla Engineering College, Bapatla, delivered a talk on machine learning models. On the second day, Dr. K.N.V.V. Prasad Garu, Assistant Professor, Department of Mathematics, Guru Gastas Viswavidyalaya, a Central University, Bilasapur, delivered a talk on the problem of discontinuity at a fixed point. On the third day, that is yesterday, Dr. C. Pavan Kumar Garu, Faculty in Mathematics, Apex Maxwell Center, North Carolina, USA, delivered a talk on applications of linear algebra in machine learning. And Dr. N. Fanikumar Garu, Professor and Head, Department of Mathematics, Vijnan Institute of Technology and Science, Hyderabad, delivered a talk on Introduction to Mathematical Modeling in Ecology and Epistemology. For the above 3 days, each session is engaged approximately with 700 participants. Thank you, one and all, for your good response and valuable support. Now, I request our head of the department and convener of this International Faculty Development Program, Dr. KVL Acharya Garu, to address the participants.
Hello. Dear faculty members, good evening to all. We have successfully completed 3 days
Hello. Good evening, sir. Voice not clear.
Sir, please wait, sir. Dear participants, please wait. Within 2 minutes, we'll connect it. Dear participants, please wait. All the participants are requested to mute your mic and video. All the participants, please mute your mic and video. Within 2 minutes, definitely will connect to you. Please wait. Dear participants, please wait.
Okay, sir.
Can we start, sir? Karunakar garu, I think it has some network issue. Can you hear my voice, Karunakar sir?
Yes, sir.
Yes, sir.
It's now okay.
Thank you. Sir, can I start to give my message?
Yes, sir, you can start.
Okay. Thank you, sir. Dear faculty members, good evening to all. We have successfully completed 3 days of our International Faculty Development Program with valuable support and punctual presence our participants. I am expecting the same cooperation and valuable support for the remaining sections also. I feel a sense of accomplishment and enthusiasm for the journey we have undertaken together. Our collective decision to growth and learning is truly commendable. It is my duty to extend my deepest gratitude to our resource persons who enriched us with their valuable and insightful talks for the last 3 days. We all know that the integral role of mathematics play in shaping and advancing various fields, underscoring its importance as a fundamental tool in the field of science and technology. Mathematics finds applications in a wide range of fields, demonstrating its versatility and significance in various aspects of life. It provides the foundation for advancements in many fields. Thus, any field is directly linked with mathematics and its applications. Hence, mathematics equips us with the ability to analyze and solve the problems. It mainly teaches us how to approach challenges logically for the purpose of overcoming hurdles with suitable and appropriate solutions. FDPs in applications of mathematics serve a key role in society's development and professional progress of our teaching community, eventually contributing to the overall supremacy of educational institutions. Today, we have a wonderful resource person with us. The resource person for today's session is Dr. P. Anuradha Kameshwari Garu, Professor, Department of Mathematics, Andhra University, Visakhapatnam. Dr. P. Anuradha Kameshwari Madam is not only a professor, but also a source of inspiration, guidance, and unwavering support to the students' community. In the vast ocean of academia, there are certain individuals like Madam who stand out as beacons of knowledge and wisdom. On behalf of the Department of Mathematics, I express my gratitude to today's esteemed resource person, Dr. P. Anuradha Kameshwari Madam, for graciously accepting our request to deliver her valuable lecture in our International Faculty Development Program. Thank you very much, Madam. Finally, in the fourth day's session, I strongly believe that we will be enriched with the lecture given by our resource person for enhancing our knowledge on solving minimal solution of Pell's equation using lattice reduction. Thank you, one and all.
Thank you, sir. Today is the fourth day in the 5-day International Faculty Development Program. And today's speaker is Dr. P. Anuradha Kameshwari Garu, Professor, Department of Mathematics, Andhra University, Visakhapatnam. Now I request one of our staff organizers, Ms. K. Sunita, to present profound profile of Dr. P. Anuradha Kameshwari Garu.
Good evening all. Welcome you all to a 5-day International Faculty Development Program on applications of mathematics in various fields with innovative approaches. I feel it a great honor to introduce today's resource person, Dr. P. Anuradha Kameshwari Garu. Dr. Anuradha Kameshwari Garu is one of the senior most professor working in the Department of Mathematics, Andhra University, Visakhapatnam. She did her MSc, MPhil and PhD in mathematics from University of Hyderabad. She qualified joint CSIR net both for JRF and lectureship in the year 1993. She has published 36 research papers in various reputed international journals. 11 students obtained PhD and 6 students got MPhil under the guidance of Dr. Anuradha Kameshwari Garu. She authored 3 lecture notes for School of Distance Education, Andhra University, and 3 international books to her credit. She is an editorial board member and reviewer for reputed journals. She is a principal investigator of the UGC Major Research Project during 2015 to 18. Presently, Dr. Anuradha Kameshwari Garu working in the areas of number theory and cryptography. Professor P. Anuradha Kameshwari Madam is praised by one and all with her best way of teaching and commendable research in advanced topics for the last 2 decades. Moreover, she made valuable service to the university as an assistant principal and warden. Her helping nature, motivational behavior, teaching abilities, research capabilities are additional strengths apart from her goodness and vast experience in the field of education and research.
Thank you, Ms. Sunita, for your nice introduction about Dr. P. Anuradha Kameshwari Garu. Now I hand over the session to Dr. P. Anuradha Kameshwari Garu. Madam, please start the session, madam.
Yeah. Good evening, sir. Thank you very much for a few nice words from you. And I feel honored to be associated with 103rd birth anniversary celebrations of Komaruvali Chandrasekharan Garu, a legendary mathematician, a founder member of TIFR, and I really feel honored to be associated on this occasion. And I appreciate the efforts of the faculty of engineering college for arranging this particular to motivate the younger generations towards research in advanced topics. So I basically come from number theory and cryptography. I want to serve the purpose of the FDP, that is motivate you towards the research in these areas. So I have selected the topic of finding solutions, a topic in number theory, solutions of Pelconics. Pelconics have lots of applications in cryptography, which actually Pelconics is like Foreman's elliptic curves. Like whatever research you want to do on elliptic curves can be experimented on Pelconics. So there is lots of research on Pelconics as well. So in that context, Pelconic study has also become important. So now the study is basically on finding the solutions. So though you have several methods to solve this solutions, one is interested in finding efficient solutions in an efficient manner. So let me just share my screen and start the topic. So this is the topic, solving minimal solution of Pell's equation using lattice reduction. So in this context, you will be introduced to three areas. One is about Pell's equation, and the other is the continued fraction methods, and then lattice reduction methods. These are the contemporary research areas. Lattice reduction is the contemporary research area, and introduction to such topics will definitely motivate you towards the research. So this is the abstract. I just want to cover the equation of the form x square minus n equal to 1, where n is a non-square positive integer, is called a Pell's equation. Solutions of Pell's equation has applications in constructions of crypto systems. So as I'm talking about in cryptography, crypto systems play a role. So because of crypto systems, the study of solutions of Pell equations has become important. Pell's equations always has a solution in natural numbers, and there are several various methods to obtain these solutions, and several mathematicians like Brahmagupta, right from Brahmagupta to Euler and etc., and the latest mathematicians as well, have all contributed to solutions. This particular presentation, I would want to introduce solutions using adapting the method of lattice reduction, and we also describe this with an algorithm. So what is the context of study? Why this study of as an introduction, I would want to talk about why this study. The study of algorithmic problems of number theory in works of Diophantine, Fermat, Euler, Gauss, Chebyshev. These all play a vital role in cryptographic applications. Like you have solutions of several Diophantine equations. Diophantine equations are the equations which talk of integer solutions. You have several Diophantine equations, and you know Euler and Fermat, who have contributed a lot to number theory, and Gauss, the modular theories. Chebyshev has contributed his role in talking about sequences and relations like Lucas, Fibonacci, and all that. Chebyshev has lots of role in that. So all their studies contributed in the works of number theory, and at present all these works have vital role to play in cryptographic applications. So cryptography is basically the tool that is used to protect information, being either national or private. A private sector. So this you protect information using crypto systems, and there are several crypto systems which are named as classical and public, and they are used in applications such as email, e-banking, etc. So now any basic book on crypto systems, cryptography shall give you the introduction on cryptography. Like Neil Koplis, you have Introduction to Cryptography by Bachman. You have references here at the end, which you can refer for the basics in cryptography. So now the other The other thing we want to introduce, involved is the lattice reduction. The LLL lattice reduction is a basis reduction algorithm given in 1982 by the three mathematicians Lenstra, AK, Lenstra Jr. and Lowas. This is given in the reference, plays a vital role in the development of fast algorithms in number theory. Number theory has several applications in cryptography, and once you are talking about applications in cryptography, one would want to have a efficient algorithm. So the efficient in the sense you want computations to be done fast. So this particular basis reduction algorithm is used in such cases. So a lattice is. Now, what is a lattice? A lattice is similar to vector space. There you talk about some axioms of vectors over a field F. Here, the restriction is you don't consider the field F, you consider it over integers. So a lattice is similar to vector space with minor restriction in multiplication of vectors by integers. And this leads to several variations. The study of reducing the basis of a lattice using LL algorithm has several applications in number theory. It is also used in computing GCDs, normal forms, solving quadratic polynomials, computing class groups, solving short vector problems, close vector problem, factoring problem. There are several applications. You can, some of them are named here. So now the point is LL algorithm is what exactly is? It is an iterative algorithm that transforms a given basis into a reduced form. It is a process to obtain a orthogonal basis. So in the process of this reduction, the problem of finding a non-zero vector that minimizes there in this process you find a problem of finding non-zero vector that minimizes its Euclidean norm. That particular problem is handled in the reduction. So this problem is the problem where you find a vector which minimizes the Euclidean norm is called the problem of short vector. So short vector problem. So it is basically denoted as SVP. So this reduction algorithm, LLL algorithm, actually solves this SVP, and it solves within a factor. C power n, where n is the dimension of the lattice. So LL algorithm actually solves your SVP in small dimensions, but in higher dimensions it is not efficiently solvable when solving the short vector problem. So you have certain difficulty of identifying the short vector when your dimension increases. So this difficulty is also used in the construction, is the basis of latest research that computing that short vector problem in higher dimensions is difficult, is hard. So that is basically the positive aspect one is going to use in the construction of the current crypto systems. They are like crypto systems like Ajitai Divak crypto system, and they are also by Goldrich, Goldwasser, Halvey, and NTRU systems. They are all based on the difficulty of this computation. So lattice reduction actually plays a vital role in the study of cryptanalysis of certain crypto systems. Cryptanalysis is basically breaking the crypto system and to obtain the actually communicated message. Okay, so lattice reduction plays a vital role in the study of crypto analysis, and there are studies by Bonnet and Durkee in 2000 using the lattice reduction, Bloomer and May in 2002, Weger and Shubhanamitra and Shantanu Sarkar in 2008, and myself and Josna, my scholar, we have handled our major research project of DST, refining RSA attack bounds. That's also basically based on lattice reduction in topics. That is in 2018. And we have also talked about this particular application to Pelconics and other things with Sundari in 2019. So the references are provided at the end. So the study of rational approximations of a real number. So basically, what exactly we want to talk about. So why this LL algorithm is going to help us. So basically, we know that the study of rational approximations of real number is called Diophantine approximation. LL algorithm can be effectively used in obtaining these Diophantine approximations. A set of rationals in a dense set is a set of, in the set of real numbers. For any arbitrary small epsilon greater than 0, we know that there exists infinitely many rationals P by Q such that P by Q is close to your alpha. Okay, so then P by Q are called the rational approximations of this real number alpha. Okay. These approximations are classified according to the absolute differences at good, best, and bad approximations. The theory of now these best approximations can be of a real number can be obtained by method of continued fractions. So in the continued fraction thing, these approximations are obtained as convergence. So in lattices, smaller dimension convergence may be computed as short vectors. So this is how where you are connecting your best approximation to convergence through continued fractions, and then you are connecting it to short vectors in LL. So this actually leads to a study of rational approximation via lattice reduction. So this is actually we are trying to link up why our lattice reduction is connected to solving solutions. Yes, sir, any problem? Okay. So we are also talking about why the study of Pelconic, why the study of solutions of Pell equations. So basically, we are trying to here give you a little gist of this. So solutions of Pell equations play a vital role in constructions of the system. Pell's equation can be solved by using continued fractions, but it is important to compute solutions of. I've been telling you that you can compute the solutions. You have several methods, but one is interested in obtaining these things efficiently in a reduced time. So we are trying to say that you can do it in context by adapting lattice reduction and obtain the solutions of equation. Here we are just going to introduce what is the continued fraction. A rational number Q. So I am trying to introduce you to each of these things. What is continued fraction? What is convergent? What is your approximation? What is the short vector? And how it is connected to your solution of Feldstone. So I need to introduce you to. I lead you to that solution through these things, continued fraction and all. So we start off with the continued fractions. A rational number Q in Q is said to have a finite continued fraction. So if Q can be, you have a reference there. So if Q can be expressed as this particular way, what it is. Okay. So where A0 is an integer, AI's are positive integers and I greater than 0, and AI's are called the quotient. And the continued fraction for Q, this continued fraction is denoted as with a box on all the quotients. Okay, so now for example, you can take the rational number and by Euclidean algorithm, you can divide your 1919 with 919 and write the quotient and the remainder, and you repeat this with 919 and 81 and repeat this and so on until you get the GCD 1. Okay, so now what you do after this, how do you get the continued fraction for that particular rational number? So now that you have this is equal to 2 plus 81 by 919, I can write it as 2 plus 1 by 911 by 81. 91 by 81 shall be equal to 11 plus. So we and so on proceeding. I will have my continued fraction with 2, 11, 2, 1, 8. So this is the continued fraction you see each time, and it can be written as this is the continued fraction for your rational number. Okay, so this is the theorem which says that every rational number. So here you are saying, see, for this continued fraction, you have only. So when you are saying it is a rational number, you are saying you are stopping at some point n. That means you are saying that your continued fraction is finite whenever your number is a rational number. So you have a theorem which asserts this. That is, every rational number has a finite continued fraction, and conversely, every finite continued fraction is a rational number. Now you have this for irrational number. An irrational number, yes, is said to have an infinite continued fraction. If this continues, n goes to infinity, it continues. Your an does not, the quotients does not stop anywhere. You have such an expression and it does not stop anywhere. And we are providing an example for that. For example, you are talking about the root 10. Root 10 will have a expansion like this, continued fraction, and your pi, the irrational number, has a continued fraction exam like this. The process is described here, how you are going about. And here again, we have a theorem which asserts that every rational number has an infinite continued fraction, and an infinite continued fraction is always associated to an irrational number. So now basically we are trying to say how the problem of rational approximation is connected to continued fractions. So for that, you are introduced the terminology of convergent. So let Q be a rational number with the continued fraction Q equal to A0, A1, N. Then the continued fraction up to AI, up to ith place, will be called as the ith convergent of Q. So you know what it is now. Now how to obtain this? We will talk about it. So let Q be a rational number with the continued fraction. Then the continued fraction up to ith is called the ith convergent of Q, and this you can do it for all your I. Another observation we are trying to talk about is, if Q is a rational number and Qi is a partial quotient, then we have the following. It is not Qi, it is Ai. Then we have the following recurrence relations. Hi is equal to this Ai into Hi minus 1 plus Hi minus 2, and Ki is equal to this, where you start with H minus 1 as 1, K minus 1 as 0, H minus 2 at 0. The initial values are this. The initial values, when you give the initial value, substitute here, you have, by this iteration formula, you will have a recurrence relation. So this is what you are trying to say is the partial quotients have this, you the partial quotient, you have this particular recurrence relation. Now given the ith convergent of Q, then you are saying that this Ai plus 1 by is the I plus 1 convergent of Q. You are talking about the next convergent. And you have, now you have the recurrence relation you have, as you have defined using your quotients, Hi and Ki would give you your ith convergent. The formula Hi by Ki is actually your ith convergent for Q. So your recurrence relations are used this way. So you have a formula to obtain your ith convergent for any given A with the continued fraction this way. So we have another notation as Qi this, and then we are giving another lemma using this partial quotient to Qi. For any continued fraction Q, Q shall be expressed in terms of your Hi's defined above and your Qi's. You have such formulas. Now they all play their role in obtaining your approximation, finding the approximations, convergence as approximations. So what you are trying, the Ki is in the recurrence relation satisfy this property, that is, it is strictly increasing, and if Ci is the ith convergence of the continued fraction, then you have this particular relation. Similarly, you have ith convergent, the GCD of Hi, Ki. You have several theories you are developing, and they all lead to our approximation theorem. The sequence of convergence C0 to Cn of continued fraction satisfy the following infinite chain. They follow this particular relation. They're all quite interesting. Okay, and they're all found in any basic book on continued fractions. You can refer to any basic book on continued fractions for these results. And you have the result which says that if Cn is the nth convergent of a real number R, Cn is the nth convergent of the real number, A and B are integers with lying between 1 and kn plus 1, then you have this particular inequality. R kn minus hn is less than or equal to R B minus A. This is a standard lemma which needs to be established, and immediately this says that if immediately you have that gives you the theorem which says that gives you an approximation, rational approximation to your real number R using your convergence. So Cn equal to Hn is an nth convergent of real number. Then for any A, B in R, you would have this particular approximation. Okay. The main theory of rational approximation to real number is contained in the following theorem. This actually has a major role to play in other applications. So this is what you are saying. So the fundamental theorem, let R be a real number, then we are saying that R be a real number. The statement is you will always be able to find integers A, B which are co-prime, and your R is approximately so much approximation. What is the approximation? R minus A by B is strictly less than 1 by 2B square. That approximation, that proximity is described in terms of A and B. This is the advantage of this particular theorem. You see, this is the approximation, the that and tan approximation theorem. You are given a real number R, then for any AB with GCD AB equal to 1, you can always find your real number. For this real number, you have the rational number A by B so close. That is R minus AB strictly less than 1 by 2B scale. So A, and this what you are trying to say is R, then A by B is nothing but a convergent of R. This A by B is not, it is actually if and only if A by B is a convergent of R. You can see that. And so that's all. That's about the convergence and the approximation to your real number identified as convergence. So now we are trying to connect this to lattice reduction. We need some introduction regarding the lattices as well, and that is what we are doing here. So let B1, B2, Bn be vectors in Rm. They are linearly independent vectors. Then the lattice L generated by B1, B2, Bn over Z. If it is over a field F, it shall be a vector space. Now, what is it you are asking for? It is generated, the lattice, it is something like a vector space generated by these vectors, but over Z. That is, the coefficients are in integers. Okay, so your lattice is going to be something like this. It is a linear combination. Now, one is basically trying to talk about what is the basis for such particular lattice. So a basis for L is any set of linearly independent vectors that generates your L. And the dimension of L is the number of vectors in a basis for L. So this is the terminology. And you're also talking about what is a fundamental domain. The fundamental domain is such a linear combination with the coefficients lying between 0 and 1. Such a thing will be called as a fundamental domain for your lattice. And the volume of the fundamental domain is going to be same as the determinant of your, is called the determinant of the lattice L. Yeah, so it is volume. This is denoted as this. Now, what is one interested in? So we want basically one is interested in talking about a basis for your lattice, which is orthogonal. So for a vector space, you know that this is an orthogonal whenever you have B1 dot product with B1 and Bj is 0 for all I not equal to j, and for I equal to j, that is Bi, that will be product will be equal to 1. So such a basis will be called as an orthonormal basis. Now, what you know is, what we have learned in vector spaces is, suppose you have a basis which is not an orthogonal basis, you have methods which change your basis to an orthonormal basis. The point is, you have the methods like Gram-Schmidt methods, how you change your basis. You get another orthogonal basis, B1 star, B2 star, and okay. So this is the steps involved in your Gram-Schmidt algorithm, how you produce your B1 star. So that is the basic idea in this given in here algorithm of Gram-Schmidt. And now you are saying that you want to talk about the same thing for a lattice. So let B be a B1, B2, Bn be a basis for a lattice L. Then B star be an associated Gram-Schmidt orthogonal basis. So then immediately what you have is, determinant of this L is nothing but the product of Bi stars. Okay, and you have the Hadamard's inequality, which says that determinant of L is less than or equal to volume F, and it is less than or equal to product of these things. It is a fundamental domain L, and we are talking about the short vector problem. So the point here is, what is a short vector problem in your lattice? So basically the problem here is, you want to find a vector in L that has a minimum Euclidean norm. So the point is, this particular problem of finding a shortest non-zero vector in lattice L with minimum Euclidean norm is called the shortest vector problem. And you also have shortest basis problem. The point is, maximum this Euclidean norm. Okay, this is minimized. The basis Bi square. This is minimized. Then you will say that that is the shortest basis problem. And there are several problems basing on such Euclidean norm computations. It's either the basis, either the vector or the basis. So next you have the Hermite's theorem. It says that every lattice L of dimension n contains some vector B in L. See, you should be asserted before going to existence of such thing. You should be asserted for the existence of such a vector. So your theorems provide that. So every lattice L of dimension n contains a non-zero vector B in L, satisfying norm B is less than or equal to root n into some proximity. We are talking about some proximity. Okay. So basically what you have is, for a given dimension n, Hermite's constant is the smallest value such that every lattice L of dimension n contains a vector. Using the above theorem, you have contains a vector B satisfying this particular relation is maintained. So there are versions of Hermite theorem that deal with more than one vector, not even one vector. You can talk about such inequalities with more than one vector. Okay, for example, we can prove that an n-dimensional lattice always has a basis. Here you are talking about as a vector, and here you are talking about a basis. So same time it is handling the short vector problem and the short basis vector problem. So now you have your Hadamard ratio. So what is this asserting is what we are going to see. So the Hadamard ratio of the basis is defined to be this particular quantity. So Hadamard ratio satisfies, it is a value between 0 and 1, and closer that the value is to 1, the more orthogonal are the vectors in the basis. So what we are trying to say is, how do you identify whether your basis is visually, how do you identify? How do you identify that your basis is orthogonal? So one such Hadamard ratio is going to help us. Compute your Hadamard ratio using this. Identify how close it is one. If it is too close, then it is orthogonal. So that's one point. So after understanding what is the short vector problem, now we are moving to what is your LL algorithm. So the Lenstra LL algorithm is an iterative algorithm. So that transforms a given lattice basis into a reduced one. So what is it basically we want? Why is it we are reducing? Why is it we are reducing your given base? So from the given base, we are reducing it to obtain an orthogonal base. An orthogonal base and a specific method it's given for us. Your short vector problem, we will see that. So the LL reduced basis also solves, so this is what it is said, it also solves your short vector problem. So using the set, see, we have already know that I have a basis, then I can transform it using the Gram-Smith. I have another orthogonal basis, I know. But the point here is your basis, the methods you have adapted from vector spaces will not be a basis for your lattice, because there you may have the coefficients coming from non-integers. Okay, but you want here integers. So this actually method directly does not produce you with a orthogonal basis for your lattice. So that is why you are moving off to this particular LL reduction. So what you are trying to say is you have a definition now. So if your basis and if B star is the associated Gram-Smith orthogonal basis, the basis B star is said to be LL reduced if you have the following options. So what it is a basis, and B star is this, then B star is said to be LL reduced if it satisfies these two properties. Your mu I value, this value is less than or equal to half, and your bi square is greater than or equal to, and this is called the size condition, and this is called the lowest condition. So for a basis to be LL reduced, you need to have the size condition and the lowest condition to be satisfied. Okay. So and you also have another approximalities. What we are trying to say, if your reduced basis is this, then the reduced basis will be approximated these particular values, and see, they are talking about some approximatives for your vectors in the basis, and you have a theorem which says that if at all your basis you have in your hand is LL reduced basis, then you see Bj is less than or equal to Bi star into this. See, you have J less than or equal to I. So this is actually, you have, as you go from end to the first vector, each time the vector Euclidean norm is reducing. And finally, you are saying here, if you have LL reduced basis, then your B1 will be approximated by this particular value, B1 less than or equal. So what it is you're trying to say? So of all the vectors there, your B1 value is taking a smaller value. It is taking a small value. So basically, it is giving you the vector B1, and it is implying that your B1 is your short vector. So your reduced basis is actually giving you a short vector. Your B1 is the short vector. It is of minimum Euclidean norm. Okay, so this is one point, and another point given is Lenstra, this LL algorithm polynomial. That is how much time it takes, how many steps it requires to find such B, and all that discussion is done by Lenstra and Loess, and they have given the polynomial time algorithm to be so much. It takes so much time. That's altogether is a different study. The complexity of whatever method you are talking about. So this particular, this takes so much time. Okay. So big O of n square log n plus log n square log b. So any number theorist would know what is a big O. Okay. And complexity analysis is the number of operations, bit operations taken to compute whatever computations involved to find the minimum vector in your lattice reduction. So, okay. So now this is done. So what is it you are introduced to? You are introduced up to here. You are introduced to you are introduced to continued fractions. You are introduced to rational approximation by convergence. You are introduced to what is a lattice, and you are introduced to what is the short vector problem. You are introduced to what is a lattice reduction with LL algorithm. Okay. So now what we want to talk about. Now the point here is now we will see that it is not discussed here, but we will see that solutions of Pelconics are connected to approximations with your convergence. So now what we do, we want to talk about solutions of Pelconics. So now we are connecting the approximation with lattice reduction. So how is you have seen that the approximation is connected to your convergence. Now you are going to connect your approximation to lattice reduction. Once it is connected, then we would go for the Pelconics and solutions with approximation. So we are talking about, earlier you discussed about how your approximation is connected to convergence. Now we are going to discuss about in this discussion how your approximation is connected to lattice reduction. So rational approximation via lattice. Lattice approximation via lattice reduction is introduced in the that is what all I told you is done here. So now here how we connect to rational approximation to lattice reduction. For that we are introducing again the concept of quadratic form. So lattices are actually corresponding to something called quadratic form, and we are also saying that every quadratic form associated to lattice is also described in the following. How you associate a quadratic form to a lattice. So here we are actually defining what we mean by a quadratic form. Suppose you have a field characteristic not equal to 2, because you are writing it 1 by 2, you need that. Let V be a vector space over K. We say that a map Q from V to K. We have a map from Q from V to K. Okay, it's called a quadratic form. If it is linear for any lambda in K and X in V, Q lambda K, lambda X is nothing but lambda square QX. Okay, and if we define your symmetric bilinear form BXY is equal to, with respect to this mapping, half QX plus Y minus QX minus QY, then B, it's a bilinear form. If you define BXY like this, then you can check that it is a bilinear form. It is the linear, you have the linearity in X plus X dash Y is equal to this. Here you have the linearity, and you have even multiplication wise, you have the linearity. Okay, so that is what a quadratic form over your vector space is like. Now we are going to talk about in the context of lattices. So the mapping Q from L to Z given as QX is equal to the inner product X and X is called the associated quadratic form of the lattice X. So the mapping given as this way, taken X and it is the inner product XX. This is how you define your inner product. Okay. You define your inner product as this way. So we will see. So note, if B1, B2, Bx is a Z basis, then the associated quadratic form for any X, we have X will be written as X1, B1, Xn, Bn. Then Qx is equal to this Qij, where Qij is nothing but Bijj. You write in the matrix form, you can see this happening. Okay, so you need to have certain ideas regarding this. So this is what your bilinear form, or this is what your inner product, where Bij is going to be Bijs, Qij is going to be this. We will have a representation for this again. We will see. Don't. So now the matrix Q is equal to this Bij's product, and this particular matrix Qij with entries are all Qij's is called the gram matrix of the basis B1, B2, Bn. Okay. So for Q equal to Qij, then we have Qx, whatever you have defined can be written as this way. So Q is nothing but Qij. Your Qx, your quadratic form will be a product like this. Okay. If B is a matrix whose columns are coordinates of Bi's, then you note your Q is nothing but B transpose B. That's it. Okay. And what you can also see is your lattice determinant is nothing but the determinant of the basis, which is nothing but again determinant of your Q. Okay. So no. So now what you are trying to see is you have defined what is a quadratic form with respect to a lattice. Now you are saying that what you have done is you have started off with the lattice and you have given a quadratic form. Now you are talking about the reverse process. That is, you have a quadratic form with you, positive definite quadratic form. Then this gives rise to a basis. This gives rise to a basis and hence a lattice. Okay, so this gives rise to a lattice. And once you have the lattice, you already have seen that lattice would give rise to a quadratic form. So now this is telling you that whatever quadratic form you have started off with, you should be getting the same quadratic form even after generating your lattice. So how do you generate your lattice with your quadratic form? That is the theorem. This is the main theorem of what all you have. So if Q is the matrix of positive quadratic form, then okay. So if for the quadratic form your quadratic form can always be written as x transpose Q and x. So you have an associated gram matrix. So there is once you have the gram matrix, then you can always generate a B in GL and R such that Q is equal to B transpose B. That is the gram matrix of you are generating a basis. Okay, so up to if you have any other if you have see what you are trying. The second point is different. What first point is telling you that you have both are covered here. First point is telling you that Qx, you give me a lattice. The second point is telling you that I have a lattice. Now I go for gram matrix, corresponding gram matrix, and I have the quadratic form. Now this quadratic form must be connected to the quadratic form you are started off with. So this is the discussion here going on. Okay, so you can always associate you can always associate a lattice to your quadratic form. And this is the process which you are going to see in the next stages. So what you are trying to so now we are basically what you have said, I have a quadratic form, I have a lattice. I have a quadratic form. So this connection is established here. Now here we are going off to the approximation with lattice reduction. So before going to lattice reduction, what it's a approximation with respect to a quadratic form. So that is the step you are starting off with. So given any real number alpha, you want to talk about the Diophantine approximation of this alpha. So given any real number alpha, consider a quadratic form. So you are starting with alpha, you are identifying a quadratic form. You are starting with alpha and you are identifying quadratic form. You see, once you have a quadratic form, you're going to have a lattice. You're going to have a basis. Once you have a basis, you have a lattice, you know the problem of short vector. So that is how the connection is going to be. Okay, so alpha is connected to rational approximation. Alpha is now connected to a quadratic form. Quadratic form is connected to a basis. Basis is connected to short vector. So you see, you start with alpha. Your approximation of alpha is connected to short vector, is going to be connected to short vector. That is what you're going to see here. So you see, you start with given any real number alpha, consider a quadratic form qxy is equal to m alpha bar x minus y whole square, your quadratic form, plus 1 by m x square. Okay, so now for some m, okay, so where you will talk about what is this alpha bar, the basis of the corresponding. So you are saying that I start alpha and this is the quadratic form I consider. We'll describe a lattice. So you have quadratic form, you have lattice. Is it taken? And a rational approximation to alpha is obtained using lattice reduction, using the following theorem. So you see, how do you go about? If alpha is a real number, then for m is equal to something like this, 10 power s for some, okay, integer where, okay, m. You are saying with alpha bar. What is your alpha bar here? You have started off with alpha and you are using your alpha bar. So what is your alpha bar? It is a decimal approximation of alpha to precision 1 by m. That is, if I take my m to be equal to your s is 2, say 10 square, then 1 by m shall be equal to 1 by 10 square. That is 0.01. So you have two decimals. So the point here is alpha to precision of 1 by m. That is nothing but alpha considered up to 2 decimals. Okay, so that is the meaning. Alpha bar, a decimal approximation of alpha to precision 1 by m. So now once you have alpha bar and you have your quadratic form. Okay, and any short vector xy of this particular quadratic form. You see, you have defined short vector for a lattice, basis of for a lattice. Here you are saying in terms of quadratic form. So because you have a quadratic form, you have a basis, you have a lattice. So immediately, what is it you are saying? I have a alpha. Then alpha, once I have the quadratic form as now, with alpha bar, with all this, then you are saying that the short vector of this particular lattice is going to give you your approximation of alpha. What it is? It is nothing but y by x. If your short vector is xy, it is y by x. So this is the rational approximation to alpha. So here in these problems, you are dealing with lattices with 2 dimensions. So what is it you are saying? I can always, given an alpha, real number alpha, I can always obtain the approximation of your alpha as a approximation given by integers y by x, and these yx are obtained as a short vector for your lattice associated to your quadratic form qxy. So this is what you have. You see the linkage. Okay, so now once you do this, what is it we are trying to say? So basically, now what is it view? Once you have this approximation with lattice reduction, So what you have discussed here, it is the rational approximation with lattice reduction. Now you are going to see that you're going to apply this. What is it you're going to apply this to? You're going to apply this to Pelconic solutions. So you are saying that your Pelconic solutions are connected to rational approximations. So they are going to be connected to lattice reduction. So this is what you are going to see here. So what it is? Now I'm trying to depict like what are solutions of Pell equation. So in few these sentences, we are talking about this equation of the form x square minus ny square, n a non-square positive integer, they are called the Pell's equations. Pell's equation always has integer solutions. There are various, and this is all you have to refer to all these theories. And you have several methods, I told you, and there are infinitely many solutions, and you have several methods to talk about the solution. And it is Lord Broncker gave a systematic method for solutions of this by continued fractions of your root n. So this this is a non-square positive integer. So your root n is an irrational number. You can write the continued fractions of this, and you can see that the solutions of your Pelconics are obtained as convergence of your continued fraction. All the solutions of this particular Pelconic are obtained as convergence of this continued fraction. So we will see what is it. So now some more points to be identified. Why this is possible? To understand that we are talking about. So a quadratic irrational number alpha is an irrational root of. So what is quadratic irrational? So incidentally we were talking about irrational. Now we are saying what it is, a quadratic irrational. So you would say that irrational number is quadratic irrational number if it is a root of some quadratic equation like this. That is, your alpha is either this or this with plus or minus. Okay, where P and Q are integers. Where your P and Q are integers. Okay. And D is a positive integer, which is not a perfect square. Okay, then you would call your irrational number alpha as a quadratic irrational. So now you have a result which says that any quadratic irrational will always has a continued fraction. So now you are talking about for an irrational number, the approximation is a convergent. Now we are saying something more. You are restricting yourself to not all irrationals, but for quadratic irrationals. So quadratic irrationals are always telling you that it is connected to continued fraction. The continued fraction of quadratic irrational is always periodic. That is the you know that it is infinite if the quotients are infinite in number, but here you are asserted that they repeat after a certain stage. That is what periodic. So this happens whenever your irrational is a quadratic irrational. Now once you are with that, you are talking about okay. Actually, the periodicity is not okay. Later it is given. Okay, later it is used. And now we are talking about another terminology for solutions of Pell equation. The solution is said to be a minimal solution. Now we are not talking about all the solutions, but you are talking about minimal solution. So what do you mean by a minimal solution? Minimal solution is that with x, x being the minimal value. Okay, so that's called the minimal solution. The point here is all your solutions can be generated from minimal solution. That is why one is interested in generating the minimal solution. Okay, so minimal solution is what it is, and we have a theorem which says that already we were stating these things. What is it we were saying? Any solution xy of Pell's equation will correspond to a convergent. So that's a theorem. And convergent and root n. See, this is less, it's a convergent. It is approximation. Corresponds to convergent of, and this is less than or. We have seen that this happens, then x by y is a convergent is what you have said. So any solution xy of Appel's equation corresponds to a convergent with this condition. So this approximation we have seen earlier in the theorem, that this xy by y will be a convergent is what you have seen in the earlier theorems at continued fractions. So Pell-conic solution will satisfy this property, hence this shall be a convergent. Now what else you are saying? Now we are saying that if your root n, so we are basically interested in solution of Pell-conic for x square minus n y square equal to 1. So root n continued fractions are going to generate your solution. Now you are saying that you are interested in talking about the minimal solution. Now you are saying that the minimal solution, if your root n is a periodic continued fraction, so that's possible when your root n is a quadratic irrational. So that is a periodic continued fraction. Then of length L, then any ith convergent, okay, then for any ith convergent, the minimal solution is generated as this way. Is if this is an ith convergent, you are taking the AL and BL, the lth convergence. AL minus 1, BL minus 1, whenever your L is even. It is A to L minus 1, B to L minus 1 if L is odd. So to prove all this, you will use your continued fractions results thoroughly here. Okay, so this is going to be a minimal solution for Pell-conic with root n of periodic continued fraction of period L. So once you have this minimal solution, now you have all general solutions given as this way from this using this relation. You have general solution x plus y root n is equal to plus or minus x naught plus y naught root n plus or minus r. So using this particular relation, you can generate your general solutions. So now you want to say that what you have observed is, what you have observed, your Pell-conic solutions are connected to your convergence of the continued fraction for root n, which are nothing but the approximations of your root n. So now you have an alpha, that is your alpha is equal to root n. So now I want to talk about the approximation xy given by xy by a short vector of the corresponding quadratic form. So for this alpha as root n, we will generate the quadratic form like this. So we will generate the quadratic form as 2xy is equal to, using your alpha. What is your alpha now? Root n. So you will generate your quadratic form as this way. Okay. So now talk about approximation of this alpha. So we know that you can, your short vector shall be the approximation for this, and we have already seen that the convergence are approximations of alpha. So what you are trying to say is the minimal solution can be obtained as a short vector. So what is it you are saying? Such a m exists. So that is what. So you know that if you have an appropriate choice of m, then you can generate your alpha to be equal to root n. You can generate your short vector, which is an approximation of root n, which is approximation of root n means it must be related to your convergent. Okay, so now this theorem is in the following theorem, it is proved that such an m is possible. So this is what, if xy is a minimal solution of this, then you are saying that the corresponding yx is a short vector. If this is a minimal solution, then yx is a short vector. So you are generating your minimal solution of Pelconic from this short vector for this particular quadratic form, and your S must be between this range. Okay, so this is what the point we are mostly interested in, which connects our approximation alpha to lattice reduction. This is the strong theorem which is connecting your approximation to short vector. Okay, so this is what you have, and you have an algorithm how you start with and how you generate your basis and how you reduce your basis and how you obtain your short vector. You see, so you have the unimodular matrices. You were talking about the theorem how to obtain the basis once you have the quadratic form. So this algorithm is following that theorem and giving you the basis, and each time you have this B1, this is the first vector. So this must be the short vector. The short vector, if this is the short vector, then CA must be the minimal solution. Then you have the convergent C equal to AI and A equal to BI. Okay, so if you are trying to say whether if this is a short vector is a solution, if this is so, how do you go about? The point here is, once you are given n, you frame your Pell's equation. Now, how do you find the solution? You write the continued fraction of root n, you write the convergence, and you identify for every convergent, you identify whether the convergence is satisfying your equation or not, whether it is satisfying this or not. Okay, that is the process earlier you have. What is it you are saying? Once you are given n, write the convergence and identify this. If you have this, then you are saying that that particular convergent is a solution of your Pelcon. See, all convergence need not be solutions. What you are saying, your class of solutions is in convergent class. Okay, so your solutions are from that class. So how to pick your solution? So this is the way. Search in the class of convergence. You search for solutions in the class of convergence. Now what is it you are saying? You search for the solutions in the class of short vectors. Where exactly you are searching? In the short vector. You find the short vector. If it is a minimal vector, then it is going to satisfy your equation. It is going to be a minimal. So if this short vector, which is a convergent, is a solution, then you have obtained your solution. Okay, so this is the process. So the point here, what we are trying to say is, instead of searching from the class of convergence, search for solutions of your Pelconic from a class of short vectors. You have class of short vectors by varying your quadratic form. So for each quadratic form, you have a lattice, you have a basis, you have a short vector. So for each m, you are varying your m in a range. So in that particular range, if you vary your m, you vary your lattices, you vary your quadratic forms, and you have your short vectors. And you are identifying whether your short vector is a solution or not. So this is how. So instead of searching the solutions in a class of convergence, all convergence, what is it you are saying? You search only for specific convergence which are short vectors. So you are searching in a subclass. Your search is now reduced to a subclass. So it is your class of search is reduced to a smaller region. So that is the advantage of using lattices. Okay, so we have handled an example here. So you are taking n is equal to 46. See, for these computation, you need to have algorithms. Manually doing these things are really difficult. So you do have the algorithm, you have given the algorithm, run the algorithm, write the coding using any of your languages, using Sage, C, C++, or any of your languages. You can run the algorithm and you can obtain these things. So what you are trying to say, now I want to talk about solutions of x square minus 46y square is equal to 1 obtained as a form of short vector. So what is it you need to do? And you are saying that what is you search for m for how long? Here you have said that what is the range for your, here you have given what is the range for your m. See, m is 10 power s and s is this particular range. Then definitely you can reach to your yx. This is the basic theorem that is done by my scholar Bala regarding this particular range and the existence of yx. Okay, so here, so this is what, so the r will be, that is the range for your s from 1 to r, where r is equal to this. So now you can compute your r is equal to, for n equal to 46, this is nothing but 62. So for s between 1 and 62, you need to find your short vectors x naught, y naught. Okay, so what we are trying, the shortest vector. This is the minimal solution. You see, this is the minimal solution. How do you obtain this? See, the convergent, this particular solution obtained as a convergent is reduced as a short vector for m equal to 10 power s, and the corresponding unimodular matrix using your lattice reduction algorithm. You are obtaining your unimodular matrix from your basis. You are transforming, you are reducing your basis. And every time you have a basis from lattice reduction algorithm for this particular lattice of this quadratic form for alpha equal to root 10. So you just see, using all those, you have done this for, so your s is between 1 to 62, so root n bar. So every time you are trying to say this is 1 decimal, this is 2 decimals, this is 3 decimals, you see your alpha bar. This is your alpha bar, and the corresponding unimodular matrix, that is the basis, that is the orthonormal basis. So this is the short vector. Every time you find this by lattice reduction algorithm, you have your basis, your short vector AC, and your solution shall be CA. Okay, so it is a solution provided this particular value is 1. Okay, so this becomes a solution. You have your AI. See, once you have this, your AI by BI is nothing but mod C by mod A. And if this gives rise to your value 1, then it becomes a solution. So you are repeating this for several various ranges of your S. So this, in this table, it is up to 4. Nowhere it is 1. And 5, it is -5. 6, it is 3. 7, it is 3. And you see, at S is equal to 8, this has given you the value 1. And this is your convergent. Okay, so this is your solution. This is your C and this is your C. And that is what you have written here. See, this is the solution. Okay, and it is obtained for S is equal to 8. Okay, so this is what you have done. And now we are trying to see graphically what is the review you can give with this computation. The review with this computation is, the point here is the class for the search of your solution is definitely reduced. Why your class is reduced? And you can see that for your, n equal to 46 itself, how it is reduced. You see, you can plot your how it is reduced. We want to depict it. How are we depicting it? We are plotting the convergence. We are plot for n equal to 46. We are plotting the convergence bn yn. So why this? they are all these B and Y, and they all lay close to this particular line, because y by x are convergence and y by x is an approximation to root 46. So they are all close to root 46. Therefore, they lie close to this particular line. That is what you are seeing, and they can be plotted. And once you plot them, what you notice in this pictures here this picture, you are seeing this for n equal to 46. For n is equal to 46, you are trying the convergence. You are seeing the convergence. You are obtaining your m. You are taking your m to be equal to 10. M to be equal to 100. These are every time your lattice is changing, and then every time your lattice changes, you have a short vector. So these red squares are talking about the convergence, which are short vectors. They are convergence as well as short vectors. And now you see, this is a short vector. This convergent cannot be obtained as a short vector. So when you search with lattice reductions, your search is jumping from this value to this value. So you are skipping two searches. So it is reduced. And this value to such is reduced to this value to this value. And again, this value to this value. And here again, you're moving to this lattice. So you are already skipping two positions here. You are skipping two positions here. So what is it basically you are trying to say? So the such class here with lattice reductions is reduced. So that is the advantage. That is the efficiency you're going to have. So this is what we are saying. So all these square things are the convergence which are lattice, which are short vectors, and they are your minimal solutions. And once you have your minimal solution, you have all the solutions of your Pelconics. That's what you are saying. So the number of Pelconics number of short vectors here you are searching each them. They might be a solution or not a solution. So your search goes in. So here you have in this particular list, you are saying that you have 11 convergence, out of which only 6 of them are short vectors, which may lead to your minimal solution. Here, somewhere here, you obtained your minimal solution. So to go to your minimal solutions, the number of steps are reduced. And as I told you, in the study of cryptography, the efficiency is very, very important. And this is what helping us. The lattice reduction, definitely, the current research topic is going to help you in reducing your search. And this is what I wanted to talk about. And that's it. And you have all the references here. Several nice books, standard books regarding the cryptography as well as continued fractions, lattice reduction, and Pelconics solutions, and approximation study, and several other things are given in this things. So these are the books. You can just go through. And that's it. And if you have any doubts, I think I can take them now. Yes.
Thank you, madam.
Yes, I am
for your
done, sir.
lecture.
Sir, I am
Madam,
done, sir.
Thank you,
Yes,
madam,
sir.
for your lecture on solving minimal solution of Pell's equation using lattice reduction. Dear participants, whether you have any doubts, please post in the Q&A box so that madam can clarify your doubts. Dear participants, whenever you have any doubts, please post in Q&A chat box. Madam can clarify your doubts.
Where is the chat box? Chat box until they can. I don't find any.
No, not that chat box, madam. There is adjacent to that there is a Q&A.
Where it is?
Chat box పక్కనే ఉంటుంది చూడండి Q&A box.
Okay, sir.
But there is no questions, madam, actually. There are no questions. We are waiting for that. Once again, participants are requested to post their questions in the chat box, or you can unmute your mic and you can ask.
You can contact me later also for your doubts.
Okay. Yes, sir.
Hello.
I'm available on my personal mobile. Yes.
Hello, sir. Am I audible?
Yes, it's audible.
Pankaj, sir.
Yes, ma'am. Thank you so much, ma'am. The session was very wonderful. I was having some just a little doubt. You said the lattices are closely related to the quadratic forms.
Associated for every lattice.
For every lattice.
For every lattice, you have a quadratic form. You are defining a quadratic form. For the lattice,
okay, ma'am, can you
are defining a quadratic form. Okay. You are defining a mapping, and you are saying that it is a quadratic form. And you are saying that if you have a quadratic form, you can also define a lattice.
Okay, so from quadratic form, we can define lattice. Yes, that was my question, ma'am. Yeah.
Yes. So they are associated one way or the other, and you are also assured that the quadratic form you start with, you have a lattice, and from the lattice you are again giving a quadratic form. Now this quadratic form and the earlier quadratic form are one and the same. That is what you have theorems which are asserting these things.
Yes, ma'am. Thank you so much, ma'am. And one more question, sir. Do we get these presentations as a material for us to study?
Definitely, we will provide it, sir.
Yes, because today's session, I wanted to go through all the materials that the references ma'am shared. I'm looking forward to it. Thank you so much, ma'am. Today's session was very wonderful and very nice.
Thank you, sir. Thank you.
Thank you so much, ma'am. And thank you, sir, for the opportunity.
Thank you, one and all, for your good response and valuable support. Expecting the same cooperation for the remaining sessions also. Today's session concludes with a vote of thanks by co-convener Dr. T. Srinivasarao garu.
Good evening to all. On behalf of the Department of Mathematics and the participants, I would like to express our sincere gratitude to our today's resource person, Dr. P. Anuradha Kameswari garu, who presented a very good and enlightening presentation on solving minimal solution of Pell's equation using lattice reduction. Solutions of Pell's equation has applications in the constructions of crypto systems, and hence the study on efficient computation of solutions of Pell's equation has become very important nowadays. There are various ways to obtain the solutions of Pell's equation. In this presentation, Madam gave the minimal solution of Pell's equation using lattice reduction. Despite Madam's hectic schedule as the Vice Principal of the Science College in the university, Madam kindly accepted our invitation and presented a talk in today's session. Thank you, Madam, for giving such a great presentation.
Thank you, sir.
HOD, sir. Acharya garu. Please switch on your video, sir. Acharya garu.
Can you hear my voice? Sir?
Yes, yes, sir.
Yes, sir. Can you hear
Sir,
my
sir,
voice?
yes, sir.
I think I have some network issues, sir. Please carry on.
Okay, sir. Thank you, madam, for kindly accepting our invitation and gave such a wonderful presentation today. Dear participants, tomorrow our schedule starts at 3 o'clock instead of 4 o'clock. I have already put a message in both WhatsApp groups, so please join in time. Thank you, madam.
Thank you,
Can I
madam.
leave, sir?
Madam, thank you very
Okay,
much,
thank you.
madam, for your valuable lecture for us.
So today's
Thank you,
session
sir.
is over and you can leave now.
Thank you,
And
sir.
feedback links will be shared in the WhatsApp groups. It will be active for an hour. Later, it will be disabled. Thank you, one and all.
Thank you, sir.